Okay, and chapter 14 is about ocean energy. And so you know how this is a blue planet and how like what 3/4 of the surface is water. And that ocean has actually three kind of energy, all kind of energy. Like our first law of thermodynamics say what? Q minus W equal to m dot multiplied by delta H plus, that's the enthalpy, thermal energy, plus delta kinetic energy plus delta potential energy, right? Isn't that the first law of thermodynamics? The ocean has thermal, potential, and kinetic energy, all of them. And they are free, and they are waiting to be harvested. Okay, and we just need to write the equipment or design the equipment to harvest them economically, because the fuel is for free. So like all the renewable energy sources, don't worry about that the efficiency is low, even if the, and you will see now how low it can get, even if the efficiency is 3%, that shouldn't really say, tell your thing, your brain that, that sucks. No, it does not suck, because 3% of what? 3% of, I mean, if you give me 3% of Bill Gates' money, I'm gonna be very happy, and my kids and my grandkids will be very happy with 3% of
Me
Bill
too.
Gates. So if you give me 3% of the ocean energy, we will be very, very happy. Okay? So the question is not the efficiency of the cycle. It is the levelized energy of, levelized cost of energy, meaning that it's what is the price per kilowatt hour. Okay, in big thermal power plant, that cost per kilowatt hour, as we just saw, it's part also of the fuel. The fuel is, you know, for 1,000 BTU, the fuel is like $12, and then the equipment is $20. Then that make the whole thing 20 plus 12, let's call it 32. And so then you can sell it for 35, you can make yourself $30, $3 per 1,000 BTU. So in the case of the ocean, the fuel is for free, but the equipment price is expensive. So if you can design an equipment that is cheap, you can make it, and you can drop the price to a competitive price with the other thing. And in some, as we will see today, in some communities, they don't have an alternative. And so if you make a company that will sell them equipment that will make this electricity for $30 even, not $30, let's call it 30 cents, 30 cents per kilowatt hour, but they don't have alternative. The alternative is that they have to fuel diesel, oil to the generator because they live in an island in North Scotland. That actually could be competitive. So for some application, the price is not really going to be the problem. Okay? So let's start with the thermal energy first. Having this in mind, it's not the efficiency, it's the price per kilowatt hour. Where is the thermal energy coming from? Of course, the sun. The sun is heating the surface. And it doesn't heat the ocean bottom. Why? Because the water is so deep and it becomes so dark at the bottom. Becomes so dark that there are creatures living there that don't really, you have to make their own light because the light does not make it there. And actually, you don't really need to go that deep. Even within just 1 kilometer, 1 kilometer depth, you can get this much difference, 27 to 4. That's 23 degrees C. That's enough to put what in between them? A cycle, a Rankine cycle can run between this and this. Okay? So a Rankine cycle between those two temperature differences is probably not going to have great efficiency. And so what is the best Rankine, not Rankine cycle, the best power cycle ever? Carnot cycle. What's the efficiency of Carnot cycle? The TH, right? Minus TC over TH, where TH is T high and TC is T cold. Or simply, I don't memorize it like this. I personally memorize it like, I always memorize that the Carnot cycle, which by the way look like what? Look like a rectangle, right? And it go like this on a TS diagram. A funny story about me is that the first time I hear about Carnot cycle, I was actually in my first year in college. So they give us thermodynamics in our first year. And they teach us the Carnot cycle. And they kept talking about this as if it's real. And I was like, this is weird. What is this cycle? And it took me like few years until I became in the second year, to realize that this is an ideal cycle, does not really exist. But it's the ideal cycle, and it's 1 minus TL over TH, which become TH minus TL over TH, right? Same thing. But that, and of course, those temperatures need to be in what? Kelvin or degree C? Kelvin. Always remember, it has to be in Kelvin. So if I take this, and again, it's ideal cycle, but he's using it to see what's the dream, What's the upper limit of his calculation. And that's what I would encourage you to do in the project. When you are considering a heat pump, think of the cycle as a Carnot cycle, as a first trial. Tell yourself, I'm going to run this heat pump with a Carnot cycle. So for a Carnot cycle running as a heat pump, then it's not efficient. It's COP. And the COP would be TH divided by TH minus TL. It will be the opposite of this. That would be the COP. TH over TH minus TC. Okay? So if our heat pump running on Carnot cycle, heating the water from 20 to 27, the COP would be 1 over 0.067. How much is that? It's going to be 100 over 6. Let's call it 100 over 10. It's going to be 10. The COP is going to be 10 if it's a Carnot cycle. So if the swimming pool need 100 kilowatt hour, a heat pump running on Carnot cycle will only require 10 kilowatt hour of electricity. So you can design your PV panel to supply only 10% of the heat the swimming pool needs. Okay? Is it really going to be Carnot cycle? No, but this tells you what is the best case scenario. So if with that best case scenario, you figure out, man, we need 150 solar panels to run that swimming pool, assuming it's Carnot cycle. I bet when it's not Carnot cycle, I will double that number. Not going to be 150 panels. We need 300 panels. This project is not a good. Right? And we did it over like 2 lines. Okay, that's what you use this analysis for, to just basically reject one of the ideas immediately. Okay, so he's saying then 6.7% efficiency. And that temperature range actually is not everywhere in the world. Only lucky places in the world have this big range between the bottom and the top. So you can see over here, that's why China was interested. Actually, they contracted Lockheed Martin to design one of those plants for them. Just run over the ocean. Okay. And also France tried to design one over here. And you can see here in the Gulf of Mexico, maybe we can make a small one over here. But the point is you need big temperature difference between the surface and the bottom. And because the efficiency is really, this is the ideal cycle, right? So the real cycle will probably be like 3 or something. So with 3% efficiency, to come up with like a decent megawatt out of it, you probably need huge QH. If the efficiency is 3%, and you say you want 10 megawatt, or like maybe, I don't know, 500 megawatts, that it's kind of like a gas turbine. So if you want 500 megawatt and the efficiency is 3%, then the Q dot H immediately is how much? The 500 megawatt divided by 0.03. So it's multiplied by 30. So a 500 megawatt require 50,000? No, 15,000 megawatt, right? So of what? Of water, of heated water. So that is megajoule per second. So you can see this thing need to suck a lot of water in to be able to generate that much power. So those things are probably going to be really huge, right? I think, do I have a sketch somewhere over here? Yeah, it's probably going to be something like this, where this is the helicopter bed or something. Okay, so this is going to be like an oil rig in the ocean or something to give you a decent megawatt. So that is a lot of cost, right? This is gonna really be expensive to build, and that's why I mean you don't see them bobbing up all over the place. Okay, so what is the reason again? Because the efficiency is small, that require huge flow rate. But anyway, that does not prevent us from studying what is a cycle would look like and how we can calculate its efficiency. So there are two ways to do this. Okay, so one of them is called open, OTEC, and OTEC stands for Ocean Thermal Energy Conversion, because we are using the thermal energy of the ocean. So Ocean Thermal Energy Conversion System, okay? And so in this open site, it's open because it actually uses the water from the ocean. And it realized that, well, it's water, I can make steam out of it, okay? So he let the water in. Of course, maybe like you just need some kind of like meshes or screens to prevent the things from coming in. But once you get the ocean surface water, which is hot, let's say 27 degrees C, you get it at 1. How do you make steam out of it? You have to flash it. What's flashing mean? Reduce the pressure. Go from P1, which is atmospheric, you're just bringing it from the ocean surface, and you reduce the pressure in it. And once you reduce the pressure, what will happen? Some become vapor and some become liquid. The liquid go back into the ocean, and the vapor, which if you want to know this m dot, how much is m dot vapor is, it's the quality, x2. Quality of this 0.2. How do I get the quality of this 2? It's almost 0, right? I mean, 0 is here and the quality in 1 is here. How do I calculate this quality? Using this H and compare it with HF and HG, right? You know that, right? We did this before. When did we do that? Geothermal. We did exactly the same cycle. We did the flashing, exactly the same cycle before, right? And so the whole idea here is when you take this 0.1 and you flash it to whatever pressure, here is 2, this is what we call 2G, and this is 2F. And the amount of m dot that will come here, m dot G, this is x2 multiplied by m dot 1. Make sense? Whatever m dot 1 that we are sending in over here, how much is going to be vapor is x2 times m dot 1. And the x2, we get it from the fact that, how do I get my x2? Well, h2 is going to be h2f plus x2 multiplied by h2g minus h2f. This equation, the only thing that's unknown here is x2. All right? How do I know h2? Because h2 is equal to H2 is equal to H1. Why H2 is equal to H1? Why? Because it's throttling. Whenever I send it to a flash chamber, whenever I drop the pressure on it, you keep the same H. That's a throttling process. H2 is equal to H1. Okay, so this is what we do to calculate. This is what we do to calculate how much is going this way. And once it goes over here, this is the isentropic expansion. This is the expansion because of the isentropic efficiency of the turbine. And so now, if you want his turbine to run at 10 megawatt or say 100 kilowatts, that cannot be really huge. That 100 kilowatt will come from what? From m dot, that's going here, m dot g multiplied by h minus h, right? And that's how you can calculate this m dot. And if you calculate this m dot and you know the x over here, this will allow you to figure how much the original m dot 1 should be. So he will, when he give you something like this, how about this? How about the project, not the project, but the homework today will be something like this. I would like you to design something like this, and I would say we'll figure out the right pressure to drop. It's kind of optimization process when you think about it. Like I can drop the pressure too much. How is that will help me? If I take the pressure too down, what will happen? I get more vapor, but what? I don't have enough delta H here. I mean, the turbine will not have that much delta H over it. Okay, so I will tell you like design this thing. So I'll give you some condition, but then and you will repeat them in number 1. In task 2, you would say, but we also have to consider, you didn't say how much delta T you need between the condenser and the cooling water. And I'm not going to specify this, you specify this. And that will be your part 2. Why do I need temperature between the condenser water and the cooling water? Because you cannot cool something when you are at his temperature. You have to be colder than him, right? So when we said that the water can be at 4 and the surface at 27, you cannot take the condenser all the way down to 4 because you need to be cooled by 4. Okay, that was one of the free quizzes that I gave you last time too. When I told you and no one answered me. When I said, you remember? One time I said, what limit the condenser pressure? Remember I told you, like in a Rankine cycle, it's known that we need to take this as high as possible, and we need to take the condenser as low as we can. Why? Because we want our turbine to have big delta H on it. What prevents this guy from going down? The temperature of the temperature of whatever is cooling him. If you are cooling him with the river water, the river water need to leave still colder than him. If you are cooling this by the air in the cooling tower, the water in the condenser need to be hotter than the air that's cooling it. So in a hot day in Tulsa, Oklahoma, if this guy come like this and he leave like this, guess what? The condenser have to sit here. You need to sit on top of it, right? Make sense? So what determines the pressure of the condenser is the temperature of the condenser, the T saturation. See, the T and the P, you cannot mix and match. If you are condensing at 40 degrees C, your pressure is 0.07 bar, for example. You go at higher temperature, you will be higher pressure. So the way to reduce the vacuum in the condenser is to let him cool at very cold temperature. Send good cold water for him. He will condense at lower temperature and his pressure will be lower. So in that design project, I'm not gonna tell you how cold this guy is. And so you will have to say, I'm gonna limit my design by saying that I have to be 5 degrees above the colder water. This is how my condenser will have enough delta T between the cold and the hot fluid going through it. Okay, and your design would be to figure out how low should this pressure is. And you do 3 calculations, and then you go into more detail to say, now, in number, when you are actually finalizing the design, you would say, now let me think about the isentropic efficiency. And how, like, let me do the calculation much better with actual, not reversible or isentropic expansion, but real expansion. And then in the last part, you would say, I totally neglected the pump over here. When I calculated work net, I was just calculating this turbine, and I assume this pump is totally, what you will see over here in this calculation. So this example is really what you're gonna do. You're just practicing on that procedure. So in the last part, task 5, when I would say now assess your design risk, you would say, I totally forget this pump. Is that a big deal or not? Let me just calculate this pump and see how much maximum work it will take. And if it turned out this pump work is nothing, then I'm safe. If it turned out to be, like 10% of the turbine work, because the turbine is like really tiny, you'd say, that's a big risk. I think I messed up in this, or like you will need to really pay attention to how much work is done on the pump and choose the pump correctly. Good. So an open OTC system operates with warm surface at 27 and the cold water is 13 from the tip cold. No, sorry. The surface condenser is 13 because the cold water is at 11. Okay? And surface condenser water at 13 degrees C from deep cold water at 11. So the condenser is sitting at 13 and the deep water is at 11. Why I wrote 15 and 13? It should be 13 and 11, not 15 and 13. Okay. The evaporator pressure is 0.037, which is sitting at 25. So that 25 will be your design problem this week. Like, what temperature is best? Should it be 25 or should we go lower? Going lower will give us more vapor. X2 will be bigger, but at the same time, the turbine will not have enough delta H on it. Okay. So what does he want? Determine the system efficiency and the warm water and the cold water and the turbine mass flow rate. Okay, so we went through the cycle. Eta thermal is work over Q added. Okay, so the work is this guy, and the Q added is what he's doing. H2G minus H4. H2G, okay, this is like his boiler exit, which is the turbine inlet, H2G minus H4. That's where you will return things to the ocean. But there is a problem here, and that is it's not the same flow rate, right? I mean, if you do it from H2G minus H4, it's the same flow rate. But if you say from H1, that is not the same flow rate. When he's asking about how much cold water is needed to cool in the condenser, how do we do this? The steam is condensing while the cold water is going and doing this. So this is what? The first law of thermodynamics, right? So there is two designs. There is a closed design and there is open, or what they call direct contact condenser. where they spray the cold fluid and let the steam condense on it. Okay, so when you do something like this, then this is the open design kind. Then 5 go to 4 and C also go to 4. So you can see how m dot steam Hc minus H4 is equal to m dot cold water H4 minus H5. So while the water is doing 5 to 4, the steam is doing 3 to 4. In this guy, this would be totally different than this. This would say m dot delta H, and this guy will have his own m dot delta H. Okay. So the only thing in this book is that sometimes the efficiency is done really weirdly. So sometimes we do it right and sometimes we do it wrong. So let's check how did we do the efficiency. Because sometimes we don't agree. Yes, see, that's the problem I have. So he is saying that the eta thermal is work actual, of course, that's the output, over H3 minus H4. You think that's the input, heat. So when we look at H3 minus H4 in this cycle, that is 3 minus 4. That is not fair. It's not 3 minus 4. The Q added is 2 minus 4. Imagine if this was a boiler, we'll take the water from here and we'll take it all the way to 2G before we send it to our turbine. So Q added is this H minus this H, not H3 minus H4. Right? So make sure that you correct this in your notes. So this was wrong. It's not H3 minus H4, it's H2G minus H4. Okay? M dot warm water, that's M dot turbine over X2. We said that before. Good? So the evaporator or the flash chamber, or how much how could he throttle it so that he can lower the pressure? It actually sometimes to look like this. See, he's sending the water and he's sending it into a place where the pressure drop. So when the pressure drop in a diffuser like this, you will end up with vapor and liquid. The liquid will drop and the vapor can be plumbed in just by a flow separator. And that vapor will go to the turbine, yes. So by starting up, do you mean warming it up or starting up like construction and actually building it? So this actually has to do with the thermal expansion of the turbines and the boilers. And so not this guy, because the temperature is not really high, but a steam power plant like in Jinx, it takes 8 hours from cold start to until they get power, full power. 8 hours. Why? Because they have to soak the boiler and the turbine in heat before they let it actually start firing. So they need to slowly get because there's like small tolerance between the plates, and if you give them some heat unevenly, maybe one part will grow before the other, maybe the turbine will expand before the casing has a chance to expand, bad things could happen. So you really have to slowly soak it up in heat. Okay, so it has to do with how quickly does the material respond to the heating. Like in our cars, in cold days, after you finish, you park the car, you keep hearing the cracking noise, right? And like things are expanding and contracting. But I guess with a small temperature difference, maybe it's not a big deal. Okay? But you will be surprised how small the The spacing is. When I was undergrad, I told you guys that I was an intern in a big steam power plant. And that steam power plant, which has 4 units, each one of them was like 315 megawatt. So the whole thing was like 1 gigawatt. Okay. And that big power plant was supposed to turn on by itself in case the whole country get blacked out. That is the one power plant that does not need anyone to run on. It's supposed to kick in by itself without any electricity from the grid, and then it can turn on the whole country together. And it did happen 1 year. We had a blackout in the whole country. Okay, and how this guy will start from black? They have a gas turbine. Okay, and that gas turbine has a diesel generator, and that diesel generator to make it start have a back of batteries. Okay, so the battery started the diesel generator, and the diesel generator started the turbine. But when he started the turbine, how does a gas turbine look like? Big shaft, and that shaft has what on it? Has the turbine on it, and also has the compressor in it, and between them the combustion chamber, right? And what else is there on a gas turbine? A generator, right? That make electricity, right? It has to have a generator. Well, all of them are sitting on the shaft, and so the generator have a coil and a stator, like a rotor and stator. That's how you generate electricity. And you need to connect electricity to the coil. While he's rotating, he still needs electricity to go in to get the magnetic field. And so how do you do that while he's rotating? How do you deliver electricity to something that's already rotating? Help. I want one of you to invent this. What is that? A brush. Carbon brush. Carbon brush is reaching to, while the shaft is rotating, to be able to connect electricity to the thing. Well, what happened was this guy jumped a little bit, because I guess at the volt at the start or something, he jumped like, I don't remember the number, but very, very tiny. But that very tiny amount that he jumped with is enough to create an air gap. And if you have electricity and air gap, what do you get? An arc. And that arc ate a little bit of the shaft. Tiny amount, but that tiny amount was enough to make vibration. And the vibration triggered a sensor, and the sensor said, no, go, stop. And that power plant, the pride of our fleet, didn't run. And we had to wait for another power plant to run so that the whole country can start again. And so what I'm telling you this example to show you, like, the tolerance is very tiny. And so whether it's for the turbine or the pipe expansion, or you really have to be very careful with like how quickly you can start them. Okay. But in general, steam power plant take 8 hours, gas turbine take 8 minutes from start to end. From cold start until we get electricity, that's like 8 minutes, more or less. Those are good numbers to remember. 8 hours against 8 minutes. See this condenser? That is a closed loop condenser, okay? All right, I took too much of your time, but you asked me, and we'll stop here, and I'm gonna give you this as a design, kind of a design problem to solve this weekend, okay? Thank you so much.